So last time we discussed about second order reaction. Okay, if the reaction is just like this, second order reaction. If the second order reaction is just like this, then rate constant equal to 1 by T into 1 by RT minus 1 by R naught. Okay, we have seen this. Last time we deduced this. Okay, last time we deduced this. So this was the relation. This was the relation 1 by RT, 1 by R naught equal to KT. So from this K equal to 1 by T, this. Okay. So this. Now if the second order reaction is just like this, if the second order reaction is just like this, then rate constant is given by 1 by T into 1 by A naught minus B naught ln B naught into A naught minus xt then A naught B naught minus xt. Okay, so these are the two expressions last time we deduced. Rate constant of the second order reaction if the reaction is like this, rate constant of the second order reaction if the reaction is just like this. Okay, so we have deduced this, and we know this is the initial concentration of the reactant. This is the concentration of the reactant at time t. Okay, at time t. Similarly, initial concentration of A, initial concentration of B, then xt. Xt is the concentration of product formed at time t. Okay, so these are the two reactions. Now let us see one problem. Okay, let us see one problem. The decomposition of HI is a second order reaction. At 700 Kelvin, the rate constant of the reaction is 1.83 into 10 to the power minus 3 per mole per second. Rate constant is this. If the initial concentration of HI is 10 to the power minus 2 molar, calculate the concentration, after 1.68 into 10 to the power 5 second. Okay, so this is the problem. Now what has been given? It is said that decomposition of HI means this is the reaction. decomposition of HI means this is the reaction. Okay. Now rate constant is given, K is given 1.83 into 10 to the power minus 3 per mole per second. Then initial concentration is given 10 to the power minus 2 molar. Okay, 10 to the power minus 2 molar. Now you have been asked to calculate time equal to 1.68 into 10 to the power 5 second. 10 to the power 5 second. So what will be the concentration of the reactant? What will be the concentration of the reactant? So very simple, you can use this relation. 1 by RT equal to KT plus 1 by R naught. Okay, so this, so just put the values. Okay, put the values. So K equal to 1.83 into 10 to the power minus 3 per mole per second, per molar per second. T equal to 1.68 into 10 to the power 5 second, 10 to the power 5 KT plus 1 by R naught, 10 to the power minus 2 molar. 10 to the power minus 2 molar. Okay. Now just simplify. Okay. This second cancels. So it will be, if you simplify this, it will be 1.83 into 1.68 into 10 to the power 2, again 10 square, 10 to the power 4, sorry, 10 to the power 2, 10 to the power 2 plus 10 square. Okay, this is per molar. So you just simplify, then take the reciprocal. Just simplify, take the reciprocal, you will get the value of RT. Okay, so this you can do. Now let us discuss some other things. Okay, say we have seen, if the reaction is this, say this is a first order reaction, if the reaction is this, we know differential rate equation is this. Differential rate equation is this. dV by dt equal to rate constant is K, so this is Ka. Now from this we can write that dA by dt equal to minus Ke, and dV by dt equal to Ke. So from this we can write like this. This is simple. Okay. Now you see, this is the reactant A. Is the reactant. So concentration of reactant decreases. So there is minus sign. B is the product. Concentration of product increases. So there is positive sign. This is the difference. Minus sign means concentration decreases. And what does this mean? It will give a change in concentration of A per unit time. Okay, this is the change in concentration of A per unit time. This is the change in concentration of B per unit time. Okay, change in concentration of A per unit time equal to this. Change in concentration of B per unit time equal to this. Reactant minus product plus. That means if something is formed, then this will be plus. A reactant minus. Okay. Now let us see another example. Let us see another example. Say now say this is the example. Okay. This is a reversible reaction. This is the rate constant of the forward reaction and rate constant of the backward reaction. This was number 1 and this is number 2. Okay. I write like this. This is the rate constant of the backward reaction, not minus sign actually. This means backward reaction. Rate constant of the forward reaction, rate constant of the backward reaction. Now, for this reaction, if we write this dA by dt, now here you see, when the forward reaction takes place, concentration of A decreases. But at the same time, backward reaction is also taking place. If the backward reaction takes place, concentration of A increases. Okay, so concentration of A decreases, at the same time concentration of A increases. For the forward reaction, reactant is A. For the backward reaction, reactant is B. Okay, backward reaction, reactant is B. Forward reaction, reactant is A. Now, what is the change in concentration of A per unit time? What is the change in concentration of A per unit time? Okay, change means decreases, at the same time increases. Decreases means minus, increases means plus. So how we write this? Okay, minus K1 concentration of A, because this portion comes from law of mass action. This portion comes from law of mass action. Okay, in law of mass action we need only reactant, not product. Rate of reaction is proportional to concentration of reactant, not product. Okay, so for this reaction, reactant is A. So this. So due to this reaction, concentration of A decreases, but at the same time, this reaction is taking place. For this reaction, concentration of A increases. And what is the rate of this reaction according to law of mass action? Rate of this reaction according to law of mass action is this. Okay, because rate of reaction is proportional to concentration of reactant. Concentration of reactant. So what I write? R equal to some constant concentration of reactant. Okay. Okay. For the backward reaction, concentration increases. So what is the total change? Total change in concentration of A. What is the total change in concentration of A? This decrease, this increase, so this is plus. So total change will be this. হয় না নাই? এইটো ৰিয়েকশ্যনৰ কাৰণে কনচেন্ট্ৰেশ্যন ডিক্ৰিজ হৈছে, এইটো ৰিয়েকশ্যনৰ কাৰণে কনচেন্ট্ৰেশ্যন ইনক্ৰিজ হৈছে, গতিকে টোটেল চেঞ্জ কিমান হ'ব? ডিক্ৰিজ প্লাছ ইনক্ৰিজ. Okay, decrease plus increase. So for this reaction dA by dt, change in concentration of A per unit time equal to this. Similarly, if you look at this, change in concentration of B per unit time, this will be equal to, now due to this reaction, concentration increases. So this will be K1, reactant is A, K1A. Now due to this reaction, concentration decreases. Okay, so this will be minus K minus 1, reactant is B, reactant is B. Okay, so for this reaction, reversible reaction, dA by dt equal to this and dV by dt equal to this. Okay, this. Next, let us see another example. Say this is the reaction, say A, B, then C. Rate constant is K1, rate constant is K2. Now here dA by dt, with A there is only one reaction. With B there are two reactions, this and this. Again with C there is only one reaction. Okay, here with A there are two reactions, one this, so we have two terms. With B two reactions, so we have two terms. Here with A one reaction, okay, with A one reaction, so we have only one term. With B one reaction, so we have only one term. Okay, we have only one term. See, with A two reactions, so two terms. With B two reactions, again two terms. So with A there is only one reaction, and due to this reaction concentration of A decreases, so it will be minus K1, and which is the reactant is A. This. Similarly, if you write dB by dt, this will be equal to, due to this reaction concentration of B increases, so plus K1A. Okay, K1A. But due to this reaction concentration of B decreases, so it will be minus, decreases, so minus. So K2, which is the reactant, B. Yes. Again dC by dt will be equal to, which C only one reaction, and which is the reactant, B. So this will be, and this is formed, so formed means positive, K2B. Okay, so for this reaction dA by dB, there is only one reaction with A, so one term. There are two reactions with B, so two terms. Again with C only one reaction, so one term. Okay, this is how we write. Let us see one more example. This is say number 4. Okay, this is a number 4. Suppose we have a reaction like this, A, B, C. This is a K1 rate constant, K minus 1 backward, K2. Okay, K2. Now with A again there are two reactions. With B there are three reactions. With C only one reaction. only one reaction. Now if we write dA by dt, dA by dt, dA by dt, that will be equal to reactant forward reaction. So this is minus K1A. Concentration decreases, concentration increases. So this will be plus, which is the reactant? B is the reactant. B is the reactant. Okay. Similarly, dV by dt, dV by dt, that will be equal to K1A minus K minus 1B. There are three reactions, so three terms. Okay. Due to this reaction, concentration of B decreases. Again, due to this reaction, concentration of B decreases. So it will be again minus K2, which is the reactant B. Okay. Again, dC by dt, dC by dt. So only one reaction with C. So this will be equal to K2B. Because C is formed so positive. C is formed so positive. Okay. So this is how we write differential rate equations. Now let us see another reaction. Say B, C. This is a K1. Rate constant is K2. Okay. Rate constant is K2. Now once again, with A there are two reactions. So dA by dt, that will be equal to A is the reactant, concentration decreases, so minus K1A. Again reactant, concentration decreases, so minus K2A. Which B, there is one reaction only, so dV by dt equal to B is formed so positive, K1A, and dC by dt equal to K2A. So this is how we write differential rate equations for different reactions. So this will be required. No? So you must remember that, say, I repeat, say with A there are two reactions, so we will have two terms. With B there are three reactions, so we will have three terms like this. You just remember this. And which rate constant, there will always be reactant. Which rate constant, there will always be reactant, not product. Okay. So you have to remember this because this will be required. Now let me talk about chemical equilibrium. Okay. This will also be required. Chemical equilibrium. Chemical equilibrium. Suppose we have a reaction like this. Say initially concentration is maximum and concentration is 0 initially. So as time increases, say at time t, concentration of A decreases to say 80. Suppose it was 100, it may become say 20, 20, anything. So decreases. If it is 100, it may become say 20 or 30. After all, concentration of reactant decreases. and concentration of product increases. Concentration of product increases at time t. Now, rate of forward reaction. If you look at the rate of forward reaction, okay, suppose I write this as Kf, rate constant of forward reaction, Kf. So, rate of forward reaction is proportional to concentration of A. Similarly, so we get rate of forward reaction equal to Kf into A. Similarly, rate of backward reaction is proportional to concentration of B, and rate constant of backward reaction is say Kb. Kf, rate constant of forward reaction. Kb, rate constant of backward reaction. Okay, Kb. And again, what we get? Rb is equal to Kb B. For backward reaction, reactant is B. Now you see, as time passes, concentration of A decreases. So speed of forward reaction decreases. But as time passes, concentration of B increases. So speed of backward reaction increases. Speed of forward reaction decreases because A decreases. Speed of backward reaction increases because B increases. So if we show it graphically, say rate of reaction versus time. Rate of reaction versus time. Okay. Rate of reaction versus time. So for forward reaction, it will be like this. Forward reaction. This is for forward reaction. Okay. So initially, concentration of A is maximum, so speed is maximum. As time passes, speed of forward reaction decreases. Why? Because A decreases. Similarly, if you look at the backward reaction, speed of backward reaction will increase like this. Will increase like this. Okay, this is for backward reaction. Because concentration of B gradually increases, so speed of backward reaction gradually increases. Now, initially, time equal to 0. Initially, speed of forward reaction is this much. Speed of backward reaction is 0. So, speed of forward reaction is not equal to speed of backward reaction. Say 1 second, after 1 second, after 1 second. Again, speed of forward reaction is this much. Speed of backward reaction is this much. So, not equal. Say 2 second. Speed of forward reaction is not equal to speed of backward reaction. Okay? 4 second. Speed of forward reaction is not equal to speed of backward reaction. But at this time, what happens? At this time, so this is a TE. This is a T. At this time, what happens? Speed of forward reaction becomes equal to speed of backward reaction at this time. That means we are getting equilibrium. Chemical equilibrium. Chemical equilibrium means speed of forward reaction equal to speed of backward reaction. Now after this time you see, as time increases, speed of forward reaction remains equal to speed of backward reaction. এইখিনি সময়ৰ পিছত speed of forward reaction আৰু স্পীড অফ বেকৱাৰ্ড ৰিয়েকশ্যন সমান হৈ থাকে, প্ৰভাইডেড ইউ ডু নট ডিষ্টাৰ্ব ইট। সমান হৈ থাকে, সমান হৈ থকা মানে কি? চ' speed of forward reaction becomes equal to speed of backward reaction. That means KFA becomes equal to KBB. Okay? So, what does it mean? Speed of forward reaction remains the same. That means concentration remains the same. Concentration remains the same. Speed of backward reaction remains the same. That means concentration of B remains the same. After this time, that means after equilibrium is established, after equilibrium is established, concentration of A and concentration of B do not change with time. Do not change with time. Okay? That means, so we can say that after equilibrium is established, the concentrations of the reactants and products do not change with time. That means concentration of reactants and products remain constant. Concentrations of reactant product remain constant after equilibrium is established. I repeat, after equilibrium is established, concentrations of reactants and products remain constant. Do not change with time means remains constant. Okay? So at equilibrium say concentration is this. Concentration is this. Concentration of B is this. At equilibrium, concentration of A is this. Concentration of B is this. So this will be this. And these are constant terms. Do not change with time. Okay? So this thing will be required. This concept will be required. You remember. So initial concentration is constant. At equilibrium, concentrations of reactants and products are constant. So you remember this. Okay. Now let us find out the rate constant. Of reversible reaction. That means or opposing reactions. Okay. Say opposing reactions or reversible reactions. Opposing reactions and first order. So we'll discuss about first order opposing reactions or reversible reactions. First order. Well, as before, let us consider this. As if this is first order reversible reaction or opposing reaction. Initially concentration of A is this, concentration of B is 0. Okay, concentration of B is 0. At time t, concentration of A is this and concentration of B is this. And at equilibrium, concentration of A is say AE and concentration of B is say B at equilibrium. Okay. So here these they are constant, this is constant, but they are not constant. As time changes, concentration will change. সময় চেঞ্জ হোৱাৰ লগে লগে এই দুটা চেঞ্জ হ'ব, কিন্তু ইকুইলিব্ৰিয়াম হোৱাৰ পিছতো এই দুটা চেঞ্জ নহয়. ডেট মিনছ দে আৰ কনষ্টেণ্ট. অ'কে, নাও let us write differential rate equation. Let us write differential rate equation as before. Okay, say dA by dt, dA by dt, that will be equal to differential rate equation as before, that will be equal to minus k1e, rate constant is k1 and rate constant is k minus 1, okay, plus k minus 1 b, k minus 1 b, okay. Similarly, dB by dt, and that is equal to k1e minus k minus 1 b, k minus 1 b, okay. Or you see, say what is A, concentration of A? Concentration of A equal to A naught minus concentration of B. Concentration of B, obviously, because A naught will be equal to concentration of A plus concentration of B. A naught must be equal to concentration of A plus concentration of B. Okay, because matter can neither be created nor destroyed, it can be converted. So concentration of A must be equal to this. So what is concentration of A? Concentration of A equal to A naught minus B. Okay, now let me write this. This is equal to, say, K1 into concentration of A naught minus B just writing this, then minus k minus 1 concentration of B, okay, concentration of B. So what is our aim? We are going to find out an expression for the rate constant, okay. But here we see there are two rate constants, k1, k minus 1. There are two rate constants. So what we do is that we will try to replace this. We will try to replace k minus 1 in terms of k1. আমাৰ দুটা ৰেট কনষ্টেণ্ট আছে, k1, k minus 1, দুটা ৰেট কনষ্টেণ্ট আছে. গতিকে প্ৰথমতে আমি কি কৰিম, k minus 1ৰ সলনি আমি k1 লিখিব চাম. তাৰমানে we will have only one rate constant, not two rate constants. We will try to replace k minus 1 by k1, so that in the expression we have only one rate constant. Then our calculation will be easier. Okay, so this is a number 1. Once again, what is our aim? We will replace k minus 1 by k1. Okay, now you see, we have already seen at equilibrium. Equilibrium means rate of forward reaction equal to rate of backward reaction. That means k1 rate of forward reaction equal to AE equal to rate of backward reaction k minus 1 equal to into BE. Okay, this. Okay, or or we can write that, or we can write that um, uh, we have already seen, a equal to a naught minus b. We have already seen this. So a will be equal to b, a will be equal to b. Okay, so or k1 a naught minus b equal to k minus 1 b b. Hence k minus 1 will be equal to k1 a naught minus b by p. So for k minus 1 we can write this. This is constant, these are also constants, these are also constant. Okay, so everything is constant. Hence from 1 we substitute this in 1. Okay, so from 1 what we get, dv by dt equal to k1 a naught minus b minus k1. Okay, k1 into this minus this. Now for k minus 1 what I will write, for k minus 1 I will write k1 a naught minus b by b. Okay, for k minus 1, for k minus 1, for k minus 1 I am writing this. Then we have this b. Okay, so we are writing this. Now just simplifying, we can simplify this. We can simplify this. This is equal to k1 a naught, k1 a naught minus k1 b. Okay, then minus k1 a naught by b, then minus minus plus, just multiplying into b, this is into b, there is b, then this b into minus plus k1 b, it will be k1 b. Okay, so k1b cancels, so we get k1 a naught minus k1 a naught by be into b. So we get this dv by dt. Okay, now from these two expressions, I take it common, k1 a naught, I can take it common, so that I have 1 minus b by be, okay, b by be, or I can write it like this, k1 a naught into be B E minus B. So I can write like this. Okay, just simply nothing else. This. Okay, I can write like this. Now dv by dt equal to this. So we can write. Or db by be minus b. Okay, minus b equal to k1 a naught by be into dt. Okay, so we can write like this. Just cross multiplication, nothing else. Just cross multiplication, nothing else. Okay, or transformation, just transformation, nothing else. Now as before we have to do the integration. This is the number 2. As before we have to do the integration. Okay, so how to do the integration? Okay, let me write here uh, what we do that. This is a 1 by, let me write it like this, be minus b db equal to k1 a naught by be dt. Okay, so integration as before, 0 to t, time 0 to t, this is constant, so I take it out, 0 to t. So integration when time is 0, concentration of b is 0, and when time is t, concentration of b is bt, so bt. So we do this integration. Okay, now this side. Okay, let me show you the integration. Suppose we write it like this, b minus b equal to x. Suppose we write like this. Then if we do this, say differentiating, this is constant, so 0, so minus db will be equal to dx, or db will be equal to minus dx. Is that it? db will be equal to minus dx. Then this integration, you see this integration, so this is equal to x, so 1 by x db equal to minus integration, db equal to minus dx. Okay, and when b is 0, x will be equal to be. Okay, when b is 0, x will be equal to be, and when x equal when b equal to bt, when b equal to bt, so x will be equal to b naught minus bt. Okay, so integration 1 by x equal to ln x minus ln x. So we can show the integration, otherwise we can directly write it like this, minus ln be minus b limit is from 0 to bt, equal to K1 A naught K1 A naught B B into T into T. So we can get. Now you put the limits, okay? Put the limits minus ln BE minus BT minus ln BE equal to K1 A naught T BE okay, or you remove the minus bracket, then this will be minus, this will be plus. So log m minus log n equal to ln BE by BE minus BT equal to K1 A naught BE T. Okay, so from this K1 equal to BE A naught T ln BE minus BT. So we have found out an expression for the rate constant of the forward direction. Okay. Then we can find out the rate expression for the rate constant of the backward direction also, because what is K minus 1? K minus 1 equal to this. So rate constant of the backward direction. That will be equal to K1. K1 means this. BE A naught T ln BE minus BT. K1 equal to this into whole into, okay, into A naught minus BE by BE. So then we can simplify this. If we simplify this, this will cancel. Then we will have A naught minus BE by A naught T ln BE minus BT. Okay, so this is the expression for the rate constant of the backward direction. Okay, this way we can find out the rate constants. Okay, now suppose we are doing this, say K1, let me write here. Now suppose we are doing this K1 plus k minus 1, k1 plus k minus 1. Now what is k1? What is k1? K1 equal to this be a naught t, be a naught t, a naught t, ln be, ln be, b minus bt, b minus bt. So this is k1, then k2, k minus 1, k minus 1 equal to a naught minus be, a naught minus be by a naught t, a naught t, a naught t, ln be, ln be, be minus bt, bt. Okay, so this is k1 plus k2, this is k1 plus k minus 1. Okay, now we can simplify this, we can simplify this. How to simplify this? This is, we can take this common. Okay, we can take this common. What are the things we can take common? 1 by a naught t, this we can take common, 1 by a naught t, then ln be by be minus bt. So a naught t, this I can take common, then we will have here be plus a naught minus be. We will have this. Okay, we will have this. Now b cancels, so we will have a naught, we will have a naught, then a naught cancels, so we will have 1 by t ln be, be minus bt, bt. Okay, okay, a naught will cancel out, a naught will cancel out, 1 by t this. So from this or we can write k1 plus k minus 1 t equal to ln be, be minus bt. Okay, this we can. Now if we have an expression like this, if we have an expression like this, e to the power x equal to y. Suppose we have an expression like this, so we can write it in log form. Okay, log y to the base e equal to x, and log y to the base e equal to log to the base e equal to ln x. That means if we have this, we can write this, or if we have this, we can write this. Okay, so we have ln this, ln y equal to x, so we can write it e to the power x equal to y. So e to the power x, e to the power k1 plus k minus 1 t. Okay, this is equal to BE minus BT. Okay, so we can write like this, or BE, just cross multiplication, B equal to BE minus BT e to the power K1 plus K minus 1 T. Okay, and this is equal to BE e to the power K1 plus K minus 1 T minus BT e to the power K1 plus K minus 1 T. Okay, this or we can write, say BT e to the power K1 plus K minus 1 T transforming this side equal to BE. So this side, this will go there, BE into e to the power K1 plus K minus 1 T minus 1. We get this. Okay, we get this. So this side, okay, this side, then this side, we get this. Hence BT equal to BE to the power e to the power K1 plus K minus 1 T into e to the power K1 plus K minus 1 T minus 1. Okay, so we can simplify further. Nothing will happen, I think. Nothing will happen. So we get this. So we are getting an expression for the concentration of. So we are getting an expression for the concentration of B. Okay. So then we can even find out for the concentration of E also. Because what is A naught? A naught, it must be equal to AT plus BT. So AT must be equal to A naught minus BT. So you put this value of BT here and you will get an expression for AT. That means concentration of B at time t. Expression for concentration of B at time t. Similarly, expression for concentration of A at time t. So we can find out expressions like this. Okay. So this is all about your opposing reactions or reversible reactions. Okay. So up to this we have discussed these things. Okay, so next time, this is first order opposing reaction, or first order reversible reaction. Next, if we consider this type of reaction, this is called consecutive reaction. Okay, so next we'll try to find out expression for A, K1, K2 of consecutive reactions next time. Now again, this type of reaction is called parallel reactions. So here also we will consider this type of reactions and we will find out expressions for concentration of A, concentration of B, concentration of C. We will do all these things, and that will be done in the next class. Okay, so so you see this, and if you have any difficulty you can ask me. Okay, thank you.